We continue with the foundations for topology by considering infinite sets, countability, and cardinality. Okay, so we know countability, it relates with counting, right? And cardinality talks about the number of elements in a set. So how then are we saying that we can talk about countability and cardinality for infinite sets, because infinite sets are supposed to be sets that have unlimited number of elements. So here the topics we'll be considering here include infinite set countability, countably infinite sets. So it means infinite sets can be countable. Then we have uncountable sets, Cantor's diagonal arguments, cardinality, the continuum, countable unions, Cartesian products, power sets, and the continuum hypothesis. Then here we see that infinite set theory studies the different possible sizes of infinite collections. Unlike finite set, two infinite sets can have the same cardinality, even when one is a proper subset of the other. In the last video, we saw how the set of positive even numbers can have the same cardinality as the set of integers. Though set of positive even numbers is a subset of the set of integers. So the natural numbers, for instance, the integers and rational numbers all have the same cardinality, while the real numbers have strictly larger cardinality. So the central idea of this lesson are the cardinality of natural number is equal to cardinality of integers, which is equal to the cardinality of rational numbers, and that is equal to aleph sub 0, aleph naught, and aleph naught is less than c, and that c is the cardinality of the set of all real numbers. So the first equation expresses countable infinity. All right, so this is countable infinity, while the second one shows that the real numbers from a strictly larger infinity called the continuum. So the second equation shows that the real numbers actually form a strictly larger infinity called the continuum. So let's go ahead and look at infinite sets. So a set is called infinite if it is not finite, simply. So that a finite set can be put into one-to-one correspondence with a set of the form 1 to up to n. So you have a well-defined number of items for some positive integer n. So an infinite set cannot be put into one-to-one correspondence with any such finite set. So it has an unending number of elements. So examples of infinite sets include the set of natural numbers where you have the counting numbers starting from 1. So 1, 2, 3, 4, 5, 6, and so on. Then, of course, you have the integers, positive and negative numbers, including 0. Then you have the rational numbers, which is the ratio of two integers. So you have P over Q, where P and Q are integers, and Q is not 0, so that this can be defined. And of course, you have set R to also be infinite, because it is a set of all real numbers. So the collection of all x, such that x is a real number. Now, the most important question is not simply whether a set is infinite, but how large the infinity is. So we have infinity, and then infinity can also be in sizes. So how large is infinity? Instead, though it is infinite, but how large is it? Then finite versus infinite sets. Now, consider the finite set A, 2, 4, 6, 8. So you know all the elements. You can list all the elements of a finite set. This set contains exactly 4 elements. So the cardinality of A is 4. Now consider B, which is 2, 4, 6, 8, 10, 12, and so on and so forth. Definitely, this is a set of all positive integers. Set of all even numbers, rather, set of all positive even numbers, and that is an infinite set. So this set continues indefinitely and therefore is infinite. For finite sets like this, we can determine their size by counting their elements, just like we're able to count 4 here. For infinite set, however, direct counting is not possible. So it's not possible to count this directly. Instead, we compare infinite sets using functions, especially bijections. So this change in perspective is one of the fundamental ideas of modern set theory. So though we cannot count the elements of an infinite set individually, but we can actually use ideas in bijection to understand their size. Then we go on to talk about comparing the sizes of sets. So let A and B be sets. So a function f which maps A to B is injective if distinct elements of A are mapped to distinct elements of B. We saw that in the last video about types of functions. Thus, f of A1 is equal to f of A2 implies that A1 is equal to A2. So for f of A1 to be equal to f of A2, for an injective function, then A1 has to be equal to A2. That's a condition that every element in A must be mapped to every distinct element in A must be mapped to distinct elements in B. Then a function is called surjective if every element of B is the image of at least one element of A. That means every element in B is mapped to at least one, is mapped to one element in A. So a function that is both injective and surjective is called the bijection, which we also saw in the last video. So if there exists a bijection between A and B, then A and B have the same cardinality. So for a bijective function, so the cardinality of the domain is equal to the cardinality of the codomain. So we write the cardinality of A, which is the domain, is equal to the cardinality of B, which is the codomain. Therefore, for infinite sets, we compare sizes by asking whether their elements can be matched perfectly. Then we go ahead to talk about countably infinite sets. So those sets can be infinite, but we may still be able to count them. So an infinite set A is called countably infinite if there exists a bijection F which maps N to A. Equivalently, the elements of A can be listed as A1, A2, A3, and so on and so forth in such a way that every element of A appears exactly once. So the cardinality of every countably infinite set is denoted by aleph naught. So the symbol aleph naught is called aleph zero. So this is aleph zero. Thus, the cardinality of the set of natural numbers, for instance, of n, whatever n is here, is actually aleph zero. So countability, therefore, means that an infinite set is large enough to contain infinitely many elements, but still small enough to be completely enumerated by the natural numbers. So then we have the natural numbers now. So the natural numbers are n is 1, 2, 3, 4, and so on and so forth. Then the identity function for that is f of n, which is equal to n, is a bijection from n to n itself. So for natural numbers now, so you map every number to itself that way. Therefore, the cardinality of n is aleph zero. So the cardinality aleph zero is the smallest infinite cardinality. So this is the smallest infinite cardinality. Every countably infinite set has exactly the cardinality of aleph zero. So every countably infinite set has exactly this cardinality. Now, talking about even natural numbers, now consider the set E, which is equal to 2, 4, 6, 8, and so on and so forth. Clearly, the set of even natural numbers is a subset, a proper subset for that matter, of the set of natural numbers. So for finite set, this would suggest that E is smaller than N. However, if we define F to map the set of natural numbers to even natural numbers by f of n equals 2n. So the correspondence then is this. So the first element is 2, the second element is 4, the third is 6, the fourth is 8, and so forth. So the function can be said to be injective because f of n1 is equal to f of n2. That implies that 2n1 is equal to 2n2, and therefore n1 is equal to n2. So it is surjective because every element, every even natural number has the form 2n. Hence, the cardinality of E now also becomes the cardinality of the set of natural numbers. Though E is a proper subset of n, but they have the same cardinality because they are both infinite sets, right? And because of the injectivity, we can then say they both have the cardinality of aleph zero. So this gives one of the most important lessons about infinite sets, that the set of even natural numbers is a proper subset of the set of natural numbers, but their cardinalities are the same. Then we talk about the odd natural numbers. So consider the odd numbers 1, 3, 5, 7, and so on. Then define a set of natural numbers that's 1, 2, 3, 4, 5, 6, 7, and all that. So define a function that maps the set of natural numbers to the set of odd natural numbers. So by f of n, which is 2n minus 1. So the first few values are the first one when you put it here. So 2 times 1 minus 1, that's 1. So put 2 times 2, 4 minus 1, 3. Put this 2 times 3, 6 minus 1, 5, and then for 4 you get 7. So every odd natural number appears exactly once. So every odd number like this appears exactly once. So that's a bijection, if you like that. So as a result of that bijection, it is a countably infinite set. So therefore, we say that the cardinality of the set of odd natural numbers is equal to the cardinality of the set of natural numbers, which is aleph zero. So thus, both the even and odd natural numbers are countably infinite because of the bijection we have. Now, the integers then are countably infinite. So talking about the set of integers, now the integers are z, which is all negative whole numbers and all positive whole numbers, as well as 0. So although the integers appear much larger than the natural numbers, they can be arranged in a sequence. So if you arrange them in a sequence, you have 0, 1, minus 1, 2, minus 2, 3 minus 3, 4 minus 4, and so on. So you define a function f which maps the set of natural numbers to the set of integers by f of 1 is 0, f of 2 is 1, f of 3 is minus 1, f of 4 is 2, f of 5 is minus 2. So instead of having them like a number line, you just have positive, negative, and it goes on. And it's which one appears only once, and so on. So every integer appears exactly once. So as far as you have every integer appearing exactly once, so that talks about bijection. And if there's bijection, that means that though it is infinite, it is a countably infinite set like that. So therefore, we can say that the cardinality of the set of integers is equal to the cardinality of the set of natural numbers because of the bijectivity, and that is equal to aleph 0. So thus, all negative integers and 0 does not create a larger cardinality. So thus, adding all negative integers and 0 does not create a larger cardinality in that case. So we have a Python illustration of integer enumeration now. Enumerating the integers in a countable sequence. So you have integers. This is an initialization. So for n in range 1 to 11, so you want to get the first, that means you want to get the first 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You want to get the first 10 numbers. So if n is equal to 1, so integers append 0, then else if n divided by 2 has a remainder of 0, then you append n divided by 2. Else, integers you append minus n divided by 2 like that. And if you run this, you then get 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and then 5, and it goes on like that. Of course, if you increase this, you can actually get more. Okay, it's still coming up. Yeah, now it's done. So if you increase it to like 20, so you can go like that also. So here you now have minus 9, 10, like this. So from 0, so you can keep going. So you can keep increasing that. Imagine you make it like 30. Let's say you have it like 30. So it goes all the way to 14 minus 14 like that. So the code illustrates the mathematical idea that the integers can be systematically listed. So you can list integers systematically. So the important point is not the programming implementation itself. The mathematical result is that every integer appears somewhere in a sequence indexed by the natural number. So we have, with this indexing now, each one of these integers appears exactly one time. And as a result of that, you can form a bijection if you match it with the set of natural numbers like that. So we have a bijection, and then though it is infinite, it is a countably infinite set. So let's talk about countability and enumerability. A set is countably infinite when its elements can be completely listed in a sequence. So as far as they can list all the elements in a sequence, like you have A1, A2, A3, all the way down. So such a sequence is called an enumeration of the set. So this sequence now is an enumeration of the set. For example, this for natural numbers, you have 1, 2, 3, and so on. So it's already naturally enumerated like that. The integers can be enumerated as what we just saw: 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. The irrational numbers can also be enumerated, although their enumeration requires a more sophisticated construction. The central question for countability, therefore, is this: can every element of the set be assigned a unique natural number index? So if that can be uniquely done, then you can say it is countable. So let's talk about rational numbers now, which is a bit tricky. So the rational numbers are defined by Q, which is the collection of all P over Q, such that P and Q are integers and Q is not equal to 0. So examples include 1 over 2 minus 3 over 4, 5, 0, 17 over 9, and so on. So the rational numbers are infinite. So they are also infinite. However, they are also countably infinite. Therefore, the cardinality of the set of rational numbers is the aleph 0, which that is the cardinality of every countably finite set that we've seen so far. So this is remarkable because between any two distinct real numbers, there are infinitely many rational numbers. So density does not imply uncountability. So the rational numbers are dense in the real numbers, but they are still countable. Then we have why rational numbers are countable. So because of it's a bit trickier with rational numbers, but why are they countable? Every rational number can be represented as P over Q with integers P and Q is not equal to 0. So for positive rational numbers, we can consider pairs like PQ belonging to the Cartesian product n by n, natural number multiplied by natural number. So if you arrange these pairs in a grid now, so you can have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, all the way down, and you have 4, 1 all the way down and right and left like that. So we can then traverse the grid diagonally. So if you traverse the grid diagonally, you have 1, 1, 1, 2, 2, 1, 1, 3, 2, 2, 3, 1. So this gives a systematic enumeration of the possible numerator-denominator pairs. So some fractions are duplicates, such as you have 1 over 1 is 1, of course. Then 2 over 2 is also 1. 3 over 3 is 1. So, and then you have things like 2 over 4, which is 1 over 2. 3 over 6 will give you the same thing. So after removing duplicate representations, every positive rational number still appears somewhere. So negative rationals and 0 can then be incorporated into that enumeration. Though this is more sophisticated than the natural, odd natural, even natural, as well as even integer, but then it is still countable. So in essence, we are saying that negative rationals and 0 can then be incorporated into the enumeration. Therefore, the cardinality of the set of rational numbers is aleph 0, just like for the other ones. Then we talk about Cartesian product, natural number multiplied by natural number, right? So that's all the possible pairs of natural numbers we can have. So consider n by n, which is the collection of m and n, such that m and n are both natural. So this set contains infinitely many ordered pairs. So we can arrange them diagonally. So you have 1, 1, 1, 2, 2, 1, 1, 3, 2, 2, 3, 1, 1, 4. So it's like 1, 1, 1, 2, 1, 3, 1, 4. Then 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 4, 1. So you can just keep going like that. So every ordered pair eventually appears in the set. So therefore, the cardinality of the Cartesian product of n by n, natural number by natural number, is also aleph 0. So this result is crucial for proving that the rational numbers are countable, because rational numbers can be associated with numerator-denominator pairs. And since the numerator and denominators are both integers, then we can have that listing. And then the cardinality is also aleph 0. So we have that kind of thing here. Python enumerator of pairs. So we want to generate pairs m and diagonally. So for the pairs now, so for diagonal in range 2, 8, so we have for m in range 1 diagonal, so whatever, so in 1 diagonal, so n is diagonal minus m. So pairs now, you append m, n. So print the pairs. So if you print the pairs here, you then have 1, 1, 1, 2, 2, 1, 1, 3, 2, 2, and it keeps going until you get to 6, 1. That's where you have the 2 by 8 thing going like that. So this diagonal enumeration illustrates how a two-dimensional infinite collection can still be listed using a one-dimensional sequence. This is one of the surprising features of countably infinite sets. So the major thing we've seen about countably infinite sets is the fact that though they are infinite, but all the elements can be listed, and they can form a bijection. They can be matched with one-on-one to natural numbers. Then we go ahead to talk about uncountable sets. We'll be talking about countable infinite set the other time. Now let's talk about uncountable sets. An infinite set is called uncountable if there is no bijection between the set and the natural numbers. So every infinite set that has been countable had a bijection with the set of between it and the set of natural numbers. But for uncountable sets, there's no bijection between the sets and the natural numbers. Equivalently, then, an uncountable set cannot be completely listed as A1, A2, A3 all the way down. So the most famous example is the set of real numbers. In fact, the cardinality of the set of real numbers is greater than aleph 0, as we saw even in the beginning, because we discovered that aleph 0 is actually equal to a number, is less than a number C, which is equal to the cardinality of the set of real numbers. Therefore, the real numbers are uncountable. So for instance, this is an open interval, right? So the open interval 0 to 1 is also uncountable, right? Because between 0 and 1, you have so many values that can come in between, on a limited number of values. So Cantor's diagonal argument provides one of the most important proofs of this fact. So talking about uncountability, if an infinite set is uncountable if the set cannot form a bijection with the set of natural numbers. So in that sense, we now see that the set of real numbers forms an is an uncountable infinite set, as well as the open interval 0, 1. Now, why study the interval 0, 1 then? Why is that coming up? So suppose we want to determine whether the real numbers between 0 and 1 can be counted. Every number in 0, 1 can be represented by a decimal expansion, such as 0.314159 or 0.271828. Suppose for contradiction that all numbers in the open interval could be listed, like R1, R2, R3. So now we are trying to prove by contradiction. Cantor's diagonal argument will construct a new real number in 0, 1 that is guaranteed not to occur anywhere in this list. So this contradiction proves that no complete enumeration is possible in the open interval 0, 1. And that takes us to the idea of Cantor's diagonal argument. Suppose that all real numbers in the open interval 0, 1 can be listed. So write the supposed list as R1, that is 0 multiplied by the A11, A12, A13, A14, then R2 0.821, 822, and all that. R3, 0.831, 832, and so on and so forth. We can visualize this as this now. So you have R1 this way. So exactly what we have up here, and all the way to R4. Now, focusing on the diagonal digits, if you focus on the diagonal digits, we have A11, A1, A22, A33, A44, and so on and so forth. We construct a new number whose nth digit is different from A and N, right? We construct a new number whose nth digit is different from A and N. So constructing the diagonal number then, so if you construct x to be 0, b1, b2, b3, b4, and all that, so that's 0 point, these numbers now. So everything we've been doing here has been 0 points. So 0 point something, something like that. It's 0 point because we are talking about 0 to 1. So now focus on the diagonal digits like that. So we construct a new, okay, constructing the diagonal number now, construct x is equal to 0 point b1, b2, b3, b4. So where each bn is different from the corresponding diagonal digits, a and n. So for example, define b sub n to be 1 when a and n is not equal to 1, and 2 when a and n is not equal to 1 also. When a and n is equal to 1, then we can say that b sub n is not equal to a and n in that case. So for every positive integer n. So thus x differs from R1, x differs from R1 in the first decimal digit. So it differs from R2 in the second digital digit. It differs from R3 in the third decimal digit. And in general, x differs from Rn in the nth digital digit like that. So that's us constructing that diagonal, because b sub n is 1 when a and n is not equal to 1, and it is 2 when a and n is equal to 1. So why the new number is not on the list then? So the constructed number x cannot equal R1 because their first decimal digits differ. So it cannot equal R2 because their second decimal digits also differ, like we saw up there. It cannot equal R3 because their third decimal digits differ. So more generally, x is not equal to Rn in short. So for every n. Therefore, x is not anywhere on the supposed complete list. So, but x is still a number in the interval 0, 1. This is a contradiction then. If you can still have a number x that is listed there, that is not part, that where x is not Rn. So this is a contradiction. Therefore, our original assumption was false, that we can also find another number in that interval that is not listed, right? We can still find a number that is not listed if we want to go by the formulation. So hence, the real numbers in the open interval 0, 1 cannot be enumerated. Therefore, the cardinality of the open interval 0, 1 is greater than aleph 0. So the interval is uncountable in that sense. Now, talking about decimal representation and Cantor's argument, some real numbers have two decimal representations. For example, 0.5000 is approximately 0.5999, like that. So to avoid any ambiguity in Cantor's diagonal argument, we can construct the number using only digits such as 1 and 2. Then the constructed number never ends in an infinite sequence of nines like this. Therefore, the argument avoids the ambiguity associated with terminating decimal expansions. So the essential mathematical idea remains unchanged. No proposed enumeration of the real numbers can contain every real number. So we have a Python illustration here of diagonalization. So a finite illustration of Cantor's diagonal construction. Imagine you have numbers like 314,159, 271,828, 161,803, 141,421, 173,205. So we have the diagonal number, initialized. So for I in number, in enumerate numbers now. So you have digits is digit I. So you have to follow each digit like that. So if digits is not equal to 1, then diagonal number is incremented by 1. Else the diagonal number will be incremented by 2. So you then print the original list, and then for number and numbers, you print the new number now. And then you can now have the constructed diagonal number. So if you run this now, we have the original list is 314,159, 271,828, 1 and all that. Then the constructed diagonal number now is 11211, like that. So this 11211 is not any of this number. So the program provides a finite illustration of the diagonal idea. So it is important. So that's 1. Okay. So it is important to understand that the computer program does not prove uncountability. The proof requires an arbitrary infinite proposed enumeration. So the mathematical statement is stronger. For every possible enumeration of the real numbers, Cantor's construction produces a real number that is missing from that enumeration. So, you have all this now. So the new number produced is not any of these things. Now we then go ahead to talk about cardinality. So, of course, this is not our first time of talking about cardinality. The cardinality of a set simply describes its size in terms of one-to-one correspondence. So, for a finite set now, the cardinality of ABC is 3. For infinite sets, cardinality is determined by bijections. So, if you can clearly establish that that an infinite set is bijective, then you can determine its cardinality to be equal to the aleph 0 value. So, if there's a bijection between A and B, then the cardinality of A is equal to the cardinality of B. For example, the cardinality of natural number is equal to integers because the integers can be enumerated. Similarly, the cardinality of set of natural number is equal to the cardinality of rational numbers. However, the cardinality of natural numbers is less than the cardinality of real numbers. Thus, cardinality allows us to distinguish different sizes of infinity. So, though we can have infinity, we have different infinite sets, but some are bigger than others. So, for instance, the set of real numbers is bigger than the set of real numbers is the cardinality is higher than the set of natural numbers, integers, rational, odd natural numbers, and even natural numbers like that. So let's talk about the cardinality aleph 0. So the cardinality of the natural numbers is n aleph 0, and the following sets all have the same cardinality. So natural numbers, integers, and rational numbers, they all have the cardinality aleph 0. Therefore, the cardinality of n is equal to cardinality of z is equal to cardinality of q. So natural numbers, integers, and rational numbers, they all have the same cardinality aleph 0. So the cardinality n sub 0, aleph 0 represent countably infinite size. It is the smallest infinite cardinality. Then we go ahead to talk about the continuum. The cardinality of the real numbers is called the cardinality of the continuum. So it is denoted by C. So that's the continuum. So the cardinality of the real numbers is called the cardinality of the continuum. Therefore, C is the cardinality of R. So Cantor's diagonal argument proves that the aleph 0 is always less than the cardinality of the continuum, which is the cardinality of R of the set of real numbers. Thus, the continuum is strictly larger than countable infinity. So the continuum is strictly larger than countable infinity. So the continuum is the cardinality associated with the entire real number line. Then we have the interval 0, 1 has the continuum has continuum cardinality also. Although the open interval 0, 1 is only a small interval inside the real line, it has the same cardinality as the entire real numbers. Consider f of x equals tan pi x minus pi over 2. This function maps 0, 1 onto R like this. So it is a 1-to-1 and onto at the same time. Therefore, we say that the cardinality of the open interval 0, 1 is equal to the cardinality of R. Hence, we say that the cardinality of 0, 1 is actually equal to the continuum cardinality. This is another striking example of how infinite sets behave differently from finite sets. So the open interval 0, 1 is a very tiny range, but then it has the same cardinality as the whole real number line. So Python illustration of the continuum mapping now. So once we demonstrate the continuous mapping, we take x from 0.001 to 0.999, and then we define y, which is tan pi x minus pi over 2 that we have here, like that. Then we put all of that together, and then we see this. So see tan pi x minus pi over 2 this way. And so from minus 20 to 20, and on this other side, you have from 0 to 1, and then you see you have the mapping of 0, 1 onto the real number. So this is 0 to 1, and then you see all the values taken like that. So the graph illustrates how a bounded interval can be mapped onto the entire real line. So this is the bounded interval, but then it is mapped onto the entire real line like that. So it can continue up and down. So it's the whole real line that way. So as x approaches 0, like this, as x moves towards 0, f of x approaches, the function itself approaches minus infinity. And as x approaches 1, the function approaches positive infinity like that. So thus, the bounded interval contains enough points to have the same cardinality as the entire real number line. So then we go to talk about countable versus uncountable sets. In summary, the major examples can be summarized as follows. Natural numbers has cardinality aleph 0, countably infinite. Integers has cardinality aleph 0, that's countably infinite also. Rational numbers, the set of numbers that can be expressed as the ratio of two integers has cardinality aleph 0, which is countably infinite. Then the open interval 0, 1 has cardinality C, that's continuum cardinality, which is uncountable. Then R is also uncountable, like that. Therefore, the cardinality of N is equal to cardinality of Z is equal to cardinality of Q, and that is equal to aleph 0, which is now less than continuum cardinality, which is equal to the cardinality of R, like that. This is one of the central conclusions of elementary set theory. So this equation summarizes many of the stories you can ever tell in set theory. And then talking about countable unions of countable sets now. So you have countable infinite sets that are countable, and you also want to take their countable unions like this. So countable unions of countable sets. Suppose A1, A2, A3 are countable sets, then their union. So if you take all their union together, it's also their union will also be countable. This theorem is called the countable union theorem. So this idea is that we can arrange the elements of each AN in a sequence and then enumerate all of the elements diagonally. This result is extremely useful in proving that complicated sets are countable. So example of a countable union then, define AN to be the collection of all n. Each set AN contains A sub n contains only one element. So it is finite and therefore countable. So if you have A1, that's one, set one, a singleton of one, A2, the singleton of two, and so on. So they are union now. So if you take the union of the all singletons contain each number, so say one singleton, two all the way. So if you put them all together, you have the set of natural numbers like that. Hence, the union of AN from n1 to infinity is actually countable. So more generally, countably many countable sets can be combined without producing an uncountable set, right? So countably many countable sets can be combined without producing an uncountable set. So we have algebraic numbers also coming into the field here. So a real number is called algebraic if it is a root of a non-zero polynomial with integer coefficients. For example, square root of 2 is algebraic because it satisfies the equation. So any number, a number is real if it satisfies such an equation. So a real number is called an algebraic real number if it's the root of a non-zero polynomial with integer coefficient. For example, root 2. So when you solve this, x squared is equal to 2. That means x is square root of 2. So root 2 answers to this algebraic expression. So every rational number is also algebraic. So the set of algebraic numbers is countable. However, the set of real numbers is uncountable. Therefore, there must be real numbers that are not algebraic. So these numbers are called transcendental numbers. So real numbers that are not algebraic are said to be transcendental. Example of transcendental numbers are numbers like pi and e, the exponential value. In fact, the set of transcendental real numbers has cardinality C. So for all transcendental numbers, the cardinality is also continuum cardinality. Thus, in the precise cardinality sense, most real numbers are transcendental, like that. So proper subsets of infinite sets now. So for finite sets, if A is a proper subset of B, then the cardinality of A is less than the cardinality of B. Sure. So this rule does not hold for infinite sets. For example, the set of even natural numbers is a proper subset of natural numbers, but their cardinality is the same aleph 0. Similarly, N is a proper subset. The set of natural numbers is a proper subset of the set of integers, right? But then their cardinality is also aleph 0. Same happens for natural numbers and natural and rational numbers. Natural numbers are proper subset of rational numbers, but their cardinality is also aleph 0. However, the set of natural numbers is a subset of rational numbers. And then the cardinality of the set of natural numbers is less than the cardinality of R, because this one is aleph 0 and this is cardinality continuum. So, and we know aleph 0 is less than cardinality continuum, like that. Continuum cardinality. Therefore, subset inclusion alone does not determine cardinality for infinite sets, like that. Then we have the Hilbert Hotel. So talking about the Hilbert Hotel, it is a thought. The Hilbert Hotel is a thought experiment that illustrates the unusual behavior of infinite sets. Imagine a hotel with rooms 1, 2, 3, 4, and so on. And suppose every room is occupied. Now, suppose one new guest arrives, move the guest in room 1 to room 2, move the guest in room 2 to room 3, and continue by moving the guest in room n to n plus 1, like that. So the new arrangement becomes 1 moves to 2, 2 to 3, 3 to 4, and so on. Then room 1 now becomes available. Therefore, a completely occupied, countably infinite hotel can accommodate another guest. So this illustrates why the cardinality of n is the same thing as the cardinality of n union the singleton set containing 0. It also demonstrates why our finite intuition about size must be modified when dealing with infinite sets. That's the idea of the Hilbert Hotel. So, of course, the set is infinite. So when you move everybody from their current room, there's enough room for them, though it is infinite, but it is countable at the same time. Then talking about finite binary strings, consider the alphabet and then so you have the set 0 1 like that. The set of all finite binary strings begin with epsilon, then you have 0 1, you have 0 0 0 1 1 0 1 1, then you have 0 0 0 0 0 1 0 1 0 0 0 1 all the way to 1 1 1 like that, and so on. So for each fixed length n, there are finitely many binary strings, right? So in fact there are 2 raised to power n binary strings of length n. So since there are countably many possible lengths, the set of all finite binary strings is countable. So this fact is important in computer science because finite computer programs, finite text, and finite encoded objects can often be represented as finite strings over a finite alphabet. Then we have infinite binary sequences. Now consider infinite binary sequences such as this. You have 0 1 0 1 1 0 0 1 like that. The situation changes dramatically in this case. So the set of all infinite binary sequences is uncountable like this. So because the numbers can just go on. Suppose we attempted to list S1, S2, S3 all the way down. We could construct a new sequence by changing the first bit of S1, then the second bit of S2, the third bit of S3, and so on. The new sequence would differ from every sequence on the proposed list. Therefore, the set of all infinite binary sequences is uncountable. This is another form of Cantor's diagonal argument in that way. Then we have power sets and Cantor theorem. In the last video or so, where we talked about set theory, we looked at power sets, which is the set of all subsets of a set. So power sets and Cantor's theorem. For a set A, its power set is the set of all subsets of A. So it is denoted by power set of A. For example, if A is 1, 2, then the power set of A will contain the empty set and itself, and then all the things in between. So the power set of the set A, which is 1, 2, is the empty set, the singleton 1, the singleton 2, and the original set 1, 2. Therefore, the cardinality of the power set is 4. And from that video, we discovered that the cardinality of the power set is equal to 2 raised by the cardinality of the set itself. So the cardinality of set A is equal to 2 raised power the cardinality of A, which is 2 raised power 2, 4. So Cantor's theorem states that for every set A, the cardinality of A is always less than the cardinality of the power set of A. That makes sense. So thus the power set always has strictly larger cardinality than the original set, and that makes sense. So the power set of natural numbers now, consider the power set P of n. So Cantor's theorem gives the cardinality of n to be less than the cardinality of P of n. So since the cardinality of n is aleph 0, then we obtain that aleph 0 is less than the cardinality of n. Thus, the cardinality of n will be uncountable because this can now be like cardinality continuum. Continuum cardinality. So in fact, there's a deep connection between subsets of n and infinite binary sequences like that. So each subset can be represented by its indicator sequence. For example, you have 1 3 5, and which can be represented by 1 0 1 0 1 0 like that. So consequently, the cardinality of the power set of natural numbers is actually continuum cardinality C like that. And then talking about Cantor's theorem states that for every set A, the cardinality of A is less than the cardinality of the power set of A. So the theorem has an important consequence. There's no largest cardinality, in short. So given any set, its power set has strictly greater cardinality. For example, the cardinality of n is always less than the cardinality of the power set of n. Then the cardinality of the power set of n is less than the cardinality of the power set of the power set of n. And this process can continue indefinitely. Thus, set theory contains an endless hierarchy of increasingly larger infinities. And that talks about the idea of the Cantor's theorem. So the continuum hypothesis, then, we know that the aleph 0, which is the cardinality of all countably finite, countable infinite sets, is always less than C, which is the continuum cardinality, which is the cardinality of uncountable sets like the real number, the open interval 0, 1, and recently the cardinality of the power set of natural numbers. Though the natural numbers is countable, but then the power set is not. So the natural question is whether there exists a cardinality strictly between aleph 0 and C. That's the continuum cardinality. So the continuum hypothesis, abbreviated CH, states that there's no such cardinality. It can be written as C is equal to N1. So that's aleph 1. So here, aleph 1 denotes the smallest cardinality strictly greater than N than aleph 0. So the continuum hypothesis is one of the most famous problems in mathematical logic. Gödel and Cohen established that the continuum hypothesis is independent of the standard axioms of set theory known as ZFC, assuming those axioms are consistent. Thus, cardinality, the continuum hypothesis cannot be proved or disproved from ZFC alone. So we have example 5 now. Consider A, which is 5, 10, 15, 20. Basically, multiples of 5 on the positive side. So define F to map N to A now. So by F of N, which is 5N, so the function is injective because F of N1 is equal to F of N2, such that 5N1 is equal to 5N2. So N1 is equal to N2. So it is subjective because every element of A is a positive multiple of 5. Therefore, F can be said to be a bijection, and hence the cardinality of A is equal to the cardinality of N, which is aleph 0 in that case. Thus, the set of multiples of 5 is countably finite. The set of multiples of 5 is countably finite. So we have another example for even integers now. So consider the set -4, -2, 0, basically even integers. So we can enumerate 0, 2, -2, 4, -4, 6, -6. And if we define F mapping natural numbers to the set of even integers, then we can have Fn. It is 0 when n is equal to 1, as you have here. Then for n over 2, we have n over 2 when n is even. So for instance, if we have 2 over 2, when n is even, for even n, so that's 0, 2. So 2 over 2, we have n is 1 in that case. Then we have minus n minus 1 over 2, and n is greater than 1 is odd in that case. So the sequence begins 0, 1, -1, 2, -2, 3, -3. So multiplying the 0 terms by 2. So multiply the non-zero terms by 2 now. Then we have 0, 2, -2, 4, like that. Therefore, the even integers are countably finite. So the cardinality of E is equal to aleph 0, like we know before. Then example is 0, 1 countable. Of course, we have agreed that it is countable. No, it is uncountable rather. So suppose that 0, 1 is countable. So we are now proving by contradiction now. Then we could write x1, x2, x3 all the way and claim that every real number in 0, 1 appears somewhere on that list. So write each number in decimal form. So x1 is 0.A11, A12, A13, up to x3, which is 0.A31, A32, all that. And then we construct another y, which is 0.B1, B2, B3, where Bn is not equal to any of the ANNs we know. Then in that case, we can say that y differs from xn in its nth digit. Therefore, y is not equal to xn for every n. Thus, y is not on that list already. So this contradicts the assumption that the list contains every element of 0, 1. Hence, 0, 1 is uncountable because we still have some elements. No matter how well you list the possible elements you think there are still elements that are not in that set. Then comparing n and r. So the natural number satisfy the cardinality is aleph 0. Cantor's diagonal argument shows that the cardinality of R is greater than aleph 0. Then the cardinality of the real numbers is actually the continuum cardinality C. Therefore, the cardinality of natural number is less than the cardinality of real numbers. This proves that the natural numbers are the real numbers, and the real numbers represent different sizes of infinity. They are both infinite sets, but real numbers is more infinite than natural numbers. So the natural numbers are countably infinite, while the real numbers are uncountable. Then we have why Q is countable. Every rational number can be written as P over Q, where P is an integer and Q is natural. So thus, rational numbers can be associated with ordered pairs. So we have P comma Q belonging to Z by N, like that. So since the cardinality of integers is aleph naught and cardinality of natural number is aleph 0 rather, and the Cartesian product of two countable sets is countable. So we have that the cardinality of Z by N is actually also aleph 0. So the rational numbers form a subset of the possible numerator-denominator pairs in that sense. Therefore, we can say that the cardinality of rational numbers is less than or equal to aleph 0 since Q is infinite, and the cardinality of Q is equal, the cardinality of Q is then aleph 0. Hence, the rational numbers are countably infinite. So far we see the general idea behind Cantor's diagonal argument. Cantor's diagonal argument follows a general strategy. So assume that a complete enumeration exists, write the object in a sequence, examine the nth position of the nth object, construct a new object that differs from the nth object at that position, conclude that the new object cannot be anywhere in the original list, obtain a contradiction, which we've done a couple of times now. So the method is much more general than decimal expansions. So it can be applied to infinite sequences, subsets of natural numbers, binary sequences, and many other mathematical structures. So the central principle is a proposed complete list can be defeated by constructing an object specifically designed to escape that list. So we have some common misconceptions here. Misconception one, that every infinite set has the same size. So that is false, because we have the aleph zero is less than cardinal continuum cardinality. Therefore, there are at least two different sizes of infinity. So we have established two different sizes of infinity so far. Aleph zero for countably infinite sets, and continuum cardinality for uncountable infinite sets. So misconception two is about the fact that every infinite proper subset is smaller. Every infinite proper subset is smaller. That's false also. For example, 2n is a proper subset of n, but their cardinality is the same aleph zero. Misconception three is about the fact that rational numbers are real numbers. Rational numbers and real numbers have the same cardinality. False, because we have the cardinality of rational numbers is aleph zero, while the cardinality of real numbers is continuum cardinality. Therefore, the cardinality of rational numbers is less than the cardinality of real numbers. Then misconception four, density means uncountability. False. The rational numbers are dense in the real numbers but are countable. So, and we have misconception five, that a bounded interval must contain fewer points than the real line. And that is false, because we have that the cardinality of the open interval 0, 1 is equal to the cardinality of the whole real number line. Though this is just a segment of the real number line, and their cardinalities are both the same. That's the continuum cardinality C. So we then talk about the infinite cardinality hierarchy. At the introductory level, we have aleph zero to be less than C. So the cardinality aleph zero describes countably infinite sets such as n, z, and q. Then the cardinality C describes the continuum, which include real numbers and the open interval 0, 1. There are other cardinalities larger than the continuum. So larger than the continuum, right? So Cantor's theorem guarantees that for every set A, the cardinality of A is less than the cardinality of the power set of A. Therefore, there is no largest infinity. So the study of these different cardinalities forms a major part of set theory. So in summary, we have the following, that so for infinite set, a set that is not finite, it has elements that can not all be numbered. Then we have bijection, a one-to-one and onto function. Then we have cardinality, mathematical size of a set, countably infinite, that can be put in bijection with the natural number n. So it means you can list in correspondence with the natural numbers. Then aleph zero is the cardinality of countably infinite sets. Uncountable cannot be put in bijection with n. Then Cantor diagonal argument proves that certain infinite sets cannot be enumerated. Then continuum, cardinality of the real numbers. Then C, which that's the cardinality of R. Then Cantor's theorem tells us that the cardinality of a set A is less than the cardinality of the power set of A. Then continuum hypothesis tells us that C. No, so if you pick any n1 that is bigger than any aleph one that is bigger than aleph 0, it is still the same thing as the continuum cardinality. So the central cardinality relationship again is cardinality of natural number is equal to cardinality of integer is equal to cardinality of rational numbers, which is equal to the aleph 0, which is less than continuum cardinality, which is this cardinality of real numbers. So our key takeaways will be this: infinite sets can have different sizes. So they can both be infinite, but their sizes can be different. Two sets have the same cardinality if there exists a bijection between them. Then the natural numbers have cardinality, aleph 0. Integers have countable infinite. Integers are countably infinite, also like natural numbers, with cardinality aleph 0. Rational numbers are countably infinite with cardinality aleph 0. Then the real numbers are uncountable with continuum cardinality C. Then Cantor's diagonal argument. Okay. So Cantor's diagonal argument proves that real numbers cannot be completely enumerated. A proper infinite subset can have the same cardinality as the set containing it. Then the continuum is strictly larger than countable infinity. So aleph 0 is always less than continuum cardinality. Then Cantor's theorem tells us that the cardinality of A is always less than the cardinality of the power set of A. Therefore, there's no largest cardinality in that case. So the study of infinite cardinalities is one of the foundations of modern set theory. So final conceptual picture now, we see that the fundamental structure developed in this lesson, we have natural numbers, countable infinity, integers, countable infinity, rational numbers, countable infinity, real numbers, uncountable infinity. Therefore, the cardinality of n is equal to cardinality of z equals to cardinality of q, which is aleph 0, while cardinality of r is c, and aleph 0 is always less than the continuum cardinality, like that. So the deepest lesson is that infinity is not a single size. So infinities are in sizes, in short. So there are uncountably infinite sets, uncountably infinite sets, and infinitely many larger cardinalities beyond this. So countably infinite sets, aleph 0, uncountably infinite sets, continuum cardinality, and infinitely many larger cardinalities. That's the cardinality of the power sets of countably infinite sets or things like that. So Cantor's work transformed our understanding of infinity by showing that mathematical collections can be compared according to precise notions of size, even when ordinary counting is impossible. So here we have practice problems. So you can see problems 1 to 10 here. I won't be able to solve any of this now because yeah, we have to end this very soon. So you can see problems 1 to 10 here. So you want to try your hands on them based on the things we've done. And then we have 11 to 20. You also want to try your hands on them. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not go ahead and do that right now? And of course, click on the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, which gives you special privileges you find when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.